So in this practice, you're going to be doing problems involving the equation solving process basics, one-step equations, and some two-step equations. So, as with all of these, as in the past, you're going to present the problem, given an opportunity to find the answer yourself, and then I will go over it in the video. So the first one, solve the following equation, x plus 4 equals 9. As with all equations, we're looking to isolate the variable that's on one side of the equation. Generally, you're going to see as I go through these, I tend to make sure that that always ends up on the left. Although some equations, they have the variable on the right, and it's perfectly fine to leave it there. Just from my personal experience, I tend to make sure they're always on the left. So I might add a step or two just to make that happen. It's not 100% necessary in the long run as long as you know what x is supposed to equal. So, but right now x plus 4 is on the left-hand side, 9 is on the right, so I want to get x alone. So the plus 4 has to go, so I will do the opposite and subtract 4 from both sides. And when I subtract 4 from both sides, I get that x equals 5. Now, one of the good things about algebra, and I'm going to show this in the first few of these problems, but I'm not going to do it for all of them, but ultimately you can check your work. This becomes particularly useful when you start dealing with more complicated equations. You want to make sure that you do have the right answer. And you can always know if you have the right answer or not just by simply checking your work. So I just go back to the original equation, or in this case, it's the x plus 4 equals 9. I'm going to replace the x with the 5 and work it out and see that does 5 plus 4 equal 9? Well, yes, it does. So that's my check for that. Some of these simpler equations, do you have to do the process? No. You probably do some of these in your head. And, you could, but in the long run, we want to make sure that you know the procedures to get rid of each individual thing so that when you start doing more complicated equations, you can keep track of it and know what needs to be done during those times. So let's go on to the next one. A minus 8 equals negative 2. So now the variable is a, and it is on the left-hand side. I want to get it alone, so I'm going to add 8 to both sides. And when I add 8 to the left, of course, a is left alone. Negative 2 plus 8 does equal 6. And again, I'm going to check that just by plugging the value of 6 in to the original equation and seeing if I do get negative 2. So is 6 minus 8 equal negative 2? Yes, it is. So that checks out the answer, and therefore there's my correct solution. For the next problem, you have 17x equals 221. Try to go and solve this. Well, when you have a number 17 next to a variable like x, it's always understood that you're doing multiplication. So on the left-hand side, I actually do have 17 times x equaling 221. So in order to solve this and get x alone, I'm going to divide both sides by 17. And when I divide both sides by 17, I do get x equaling 13. Now you can do that with long division if you want to. I'm going to show some multiplication in the work, but you could also use a calculator to come up with these at times as well. It's a little bit more difficult when they want any mixed numbers or fractions, but still doable. So to go back and check out the work, I'm just going to plug in 13 in place of x. So I have 17 times 13. Does that equal 221? So when I do 17 times 13, I'm going to take 17 times 3. So 7 times 3 is 21. Carry the 2. 1 times 3 is 3 plus 2 is 5. So I have 51. I leave a space. I do 17 times 1, and I get 17. And when I add this up, I get 221. So 17 times 13 is 221. That does equal 221. So both sides agree. So that does check out. For this one, you have x over 5 equaling 4.2. Now remember for this one, when you have a fraction bar is the same thing as a division symbol. That's used most often in algebra for division. So on the left-hand side, I have x divided by 5 equaling 4.2. So if I want to get rid of a division, I'm going to do its opposite operation. I'm going to multiply both sides by 5. Therefore, on the left-hand side, I'm going to have x. 4.2 times 5 does equal 21. So, basically, for me to check this out, does 21 divided by 5 equal 4.2? So if I carry through the division, 21 divided by 5, well, 5 goes into 21 4 times. 4 times 5 is 20. I get a remainder of 1. I put decimal points in and put a trailing 0 and bring down that 0. And so 5 goes into 10 twice, and I get 4.2. So 20 over 5 does equal 4.2. The two sides do equal, so it does check out. Now, as I go through the remaining problems in this practice, you're going to see that I'm not going to provide the check for you because, one, it's something you should do on your own. You can make sure to do it on your own to verify you have the right answer before you submit it. And two, because of the fact that I'm going over this after you've done the problem, you're getting a check anyway. So you're seeing what the correct answer is. So I'm not going to go through the process of checking it for you after this point, but it's something you should definitely do in order to make sure that you do have the right answer. So moving on to the next question. C minus 3/4 equals 2/5. For this problem here, I'm trying to get C alone. C is being subtracted by 3/4. So, basically, to get rid of subtraction, I am going to add. The only thing that really complicates this is that, as I am adding fractions here. I'm adding 3/4 to both sides here. Not a big deal if you remember your fraction rules. And when we start getting more into some two-step equations circumstances, you're going to see that, at times we're going to oftentimes, get rid of fractions along the way, at least temporarily, by multiplying the entire equation on both sides by the least common denominator. That usually clears that up and makes some of the process a little easier. Still some fraction rules you have to know. But for this stage here, just me adding 3/4 to both sides, it clears up the C pretty easily. On the right-hand side, I have 2/5 plus 3/4. Now, I had to go back over my fraction rules a little bit here. And, of course, for me to add two fractions together, I do have to have a common denominator. So 2/5 and 3/4, I mean, right now they have different denominators. So a common denominator that's the smallest one for 5 and 4 would be 20. So I'm going to turn these both into 20ths. So like for this one here, if I multiply the bottom by 4 to get 20, and multiply the top by 4, I'm going to get 8 20ths. I did the same thing with 3/4. I multiply the bottom by 5 to get 20, so I multiply the top by 5 as well, and I get 15 20ths. So now 2/5 plus 3/4 goes 8 20ths plus 15 20ths. Now I can add them together to get 23 20ths. And I could leave it as that. I mean, generally, I would at the very least, simplify this if there's any common terms in this. However, 23 is a prime number. There's really nothing that's going to factor out of it other than 1 in or itself. So there's no common factors between 23 and 20. The only other way I could possibly simplify this further is to carry through the division and write that as a mixed number. And if I do that, I get 1 and 3/20ths. Oftentimes in algebra texts, you'll see this used more often. Mixed numbers don't get used quite as frequently in algebra texts, only because of the fact that students get accustomed to having things appearing next to each other, like for instance, like the 17x we did earlier, or the problem we're going to do soon. We're going to have a 6x. That usually means multiplication, and sometimes students start getting into a nasty habit of saying that this means 1 times 3/20ths, which it doesn't. It's 1 plus 3/20ths. It's a mixed number, so sometimes students misinterpret that. And so usually, if they want to have any kind of, mixed number type situation, they would tend to write it as decimals. And also, if they want it as a fraction, they would tend to keep it as an improper fraction for a solution, or at least a number that would be used for subsequent calculation as you went along with it. So moving on to the next one. 6x equals 16. Well, as stated before, this on the left-hand side is 6 times x, so I do have a multiplication here. So for me to get x alone, I am going to divide both sides by 6. And that means x is going to be 16/6, which would simplify into 8/3, which would be a suitable answer in many cases. Sometimes you'll see it written as a mixed number. It's 2 2/3. You would also tend to see it sometimes written as a decimal, because I mean, since this did not start off with any fractions or decimals, you could probably write it in either form, and sometimes it would depend upon if it's a multiple choice item, what you had as a multiple choice item. If it's in decimals or fractions, that would kind of dictate which one you're going to use. Usually, if it starts with fractions, it should end with fractions. If it starts with decimals, it should end with decimals. This could also be written as 2.6 repeating, which means basically 2.66666, with those repeating sixes going on forever. That's one of the reasons, like for these repeating decimals, they more oftentimes than not you would see this kind of preference, because it's more exact. I'm not rounding anything. I'm not cutting it off in any way. But the bar or the trailing dots after the sixes indicate that it repeats forever and ever. So that's also a way of accurately reporting that number without over rounding it. What you don't want to do for instances like this, I'll put no here, is just to say sometimes 2.7. Unless the students will tend to do that at time to time, and it's okay if you're told to round it to one decimal place. If you're not told to round it in any way, then don't round it at least that much. So, moving on to the next problem. 14 equals 3/2 times g. Well, now, a couple of things that are different here. This one actually has the variable on the right. That's not a big deal. If I wanted to, I could rewrite it with the 3/2 g on the left and the 14 on the right. You're going to see eventually I do that, because I am used to making sure to report the answer with the letter on the left, number on the right. And also here, I have a fraction being multiplied here. So, a couple of things that go along the way with this, and there's some shortcuts you could take with this. But since I do have 3/2 times g on the right, and I do want to get g alone here, I'm going to divide both sides by that 3/2. So I would do 14 divided by 3/2 on the left, and I would have 3/2 divided by 3/2 times g on the right. Now, of course, on the right-hand side, obviously these two cancel, and we're going to see that momentarily. But on the left-hand side, for me to work out that quantity there's some rules about, fractions and division I have to be aware of. First of all, 14, I'm going to probably want to write that as a fraction, as itself, an improper fraction, so I'd tend to write that as 14/1. The other thing I have to keep in mind is that when I divide by a fraction, it's the same thing as me multiplying by its reciprocal. So 14 divided by 3/2 is going to become 14/1 times 2/3. And of course the right-hand side does cancel. So now I have, the left-hand side. When I multiply through fractions, I simply just multiply the numerators and I multiply the denominators. So 14 times 2 is 28, 1 times 3 is 3, so I'm going to have 28/3. And notice here I did move the g to the left-hand side. That's an improper fraction. I could keep it that way. I could also carry through the division. And so if I do 28 divided by 3, 28, 3 goes to 28 9 times, so I would have 9 times 3 is 27, remainder of 1, and I just write that as 1/3. And that's another way I could write the final answer is 9 1/3. And I don't bother the decimal on this one only because of the fact that we started with fractions being used, therefore I'm going to tend to write this as a fraction. On to the next problem. X/4 equals 8/5, so take a moment and solve this and we'll go over it. So basically I want to get x isolated on the left-hand side. Right now x is being divided by 4, so to get rid of that division, I'm going to multiply both sides by 4. So on the left, basically the multiplication of 4 and division of 4 cancel. On the right, I'm going to rethink that as being 8/5 times 4 firsts. and I'm going to multiply across, and I get 32 over 5. I can leave that improper fraction as an answer, or I can carry through the division. And again, if I do 32 divided by 5, and you see what the answer is. But 5 does go into 32 6 times. 6 times 5 is 30. I get a remainder of 2, and that's where the 2/5 comes from. On to the next one. X minus 13/15 equals a negative 4/5. Well, so for this one, I'm trying to isolate x. It's on the left-hand side, so I'm going to add 13/15 to both sides to get rid of the subtraction. So I have x equaling negative 4/5 plus 13/15. I got to carry through that addition on the right-hand side. So what I need to do at this point is, get a common denominator. So I want to think of a number that 5 and 15 can both be factored out of. Well, 15 would be that number. So 13/15 is going to be left alone. Negative 4 over 5 is going to have the numerator and denominator multiplied by 3, and as a result of that, I'm going to end up with x equaling negative 12 over 15 plus 13 over 15, and then when I add that together, I get 1 over 15, and that's all I have to do for that one. 14 equals b plus 20. Now, again, I'm going to add a step to this because the way I've been trained over many, many, many years is that I'm used to having the variable on the left. So I'm just going to change this equation to say that b plus 20 equals 14. I'm not really doing anything of consequence by doing that, so it's perfectly allowable. I do want to get b alone, so I got to get rid of that addition of 20. So I'm going to subtract 20 from both sides of the equation. On the left-hand side, the b, of course, is left alone. 14 minus 20 is a negative 6. And that's what the answer is. So, on to the next question. This one here is a little tricky, and I make sure to kind of put this in between the end of the one-step equations and before what looks like the normal two-step equations. The reason why I'm doing that here is that this is actually a two-step equation. Students sometimes misinterpret this, and they start treating it as if this actually said L minus 9.2 equals 7.1, whereas as you can see, the way to interpret it is negative L plus 9.2 equals 7.1. These are not the same thing. And it's important because the negative sign is attached to the L. It's not attached to the 9.2. The 9.2 is positive. So here I have negative L plus 9.2 equaling 7.1. So there's actually two things I need to get rid of here. I got to get rid of the addition of 9.2, and I got to get rid of the negative sign on the L, which is the same thing as a multiplication of negative 1. So I got to get rid of that multiplication. Now, one of the conventions when you're solving equations that have more than one step is that you want to follow the order of operations in reverse, because what you're basically doing is that there's other ways of dealing with it, but you have to be more mindful of the distributive property, which causes more complications if you don't do it by following the order of operations in reverse. The reason being is that this variable has had several things done to it. Those things that are being done to it follow the order of operations. So if I want to undo it, I have to reverse the order. So that's why I follow the order of operations in reverse. So the first thing I had to do to solve for L here is that I do have to subtract both sides by 9.2. And when I do that, I get that negative L equals negative 2.1. And again, as I had mentioned before, that negative L is basically the same thing as me saying I have negative 1 times L. So I got to get rid of that multiplication of negative 1. And we deal with these negatives. Sometimes where students sometimes have other issues is that, remember, I'm not doing the opposite of the sign here. When I do opposites, I'm doing the opposite operation. So since I'm multiplying by negative 1, I need to divide by a negative 1 on both sides. And on the left, it's going to leave me with L. On the right, it's going to leave me with 2.1. So keep that in mind as you do problems like this where you have the variable in the second position in a subtraction, the one where the minus sign's attached to it, because that's a two-step equation as compared to those, where, if I had a subtraction and the variable was first in the expression on whatever side of the equal sign it is, that would tend to be a one-step equation. So this one's very similar, involves fractions, but give it a try. So for this one here, you have 8/3 equaling 2/3 minus p. And so I'm going to first, change the sides around a little bit. So 8/3, so 2/3 minus p equals 8/3. And I'm not gonna rearrange this. I mean, again, I could make it a point to say that, this I could rewrite this if I wanted to as negative p plus 2/3 equals 8/3. But if you keep in mind what the signages are and what operations are actually occurring, that's not 100% necessary. If you find that you need to write that extra step in order to make sure you're doing it correctly, then by all means add the extra step. But I do recognize that this 2/3 is being added. I do have a multiplication of -1, so the addition of 2/3 has to go away first, so I'm going to subtract 2/3 from both sides. And when I do that, I end up with negative p equaling 6/3. And 6/3, 6 divided by 3 is 2. So I'm going to simplify that, when I get a chance to do that. So I have negative p equaling 2, and again, negative p is the same thing as -1 times p equaling 2. So I'm going to divide both sides by -1, and I end up with p equaling -2. So again, these situations where you have a subtraction and the variable follows the subtraction sign, you're automatically into territory where where you have a two-step equation. Now, the remainder of these are going to be typical two-step equations. So let's have a chance to go at them. So for this one here, you have a is the variable I need to isolate. I have 4a minus 5 equaling 11. So I have a multiplication of 4 and a subtraction of 5 that's occurring to the a on the left-hand side. So those are the things that have to go in order for me to get a isolated. And again, I'm going to undo them by following the order of operations in reverse. So additions and subtractions would be eliminated first. So the subtraction of 5 goes first. So to get rid of a subtraction of 5, I have to add 5. So you have to keep in mind, make sure you don't get confused between what you need to eliminate and how you're going to eliminate it. So yes, I know I had to eliminate a subtraction of 5. How I eliminate it is by adding 5. Sometimes students along the way, they just pay attention to what they have to eliminate, and then they just rewrite that, and they'll say like -5 on both sides. Well, subtracting 5 would not eliminate a -5. It would just make that a -10. And even though if you did it on both sides, the equation is still valid, you're not closer to a solution. But here, adding the 5 would cause a cancellation between the -5 and the +5 on the left, so I end up with 4a equaling 16. And now, again, 4a means 4 times a, so I will divide both sides by 4. And when I divide both sides by 4, I get that a does equal 4. So there's your solution. On to the next one. So I want to isolate the x. It's on the left-hand side. So I do have a multiplication. I have a division of 5, and I have an addition of 7 that are attached to the x. And again, I have to eliminate those in the correct order in order to get the correct solution. So again, undoing my order of operations, I'm going to eliminate any additions or subtractions first. So the +7 has to go. So I'm going to subtract 7 from both sides. When I subtract 7 from the left, I'm left with x over 5. When I subtract 7 from the right, I get 4. Now, I have x over 5 equaling 4. Of course, x over 5 is x divided by 5. So to get rid of that, I'm going to multiply both sides by 5. When I do that, on the left-hand side, x is isolated. 4 times 5 does equal 20. So the final answer is x equals 20. Now for the next problem, you're going to see the left-hand side is going to have the same operations, but it's going to be drawn differently. And even though it's not really in the realm of a two-step equation exactly, although depending on how you treat it, it can be, um, I did want to make sure to point it out so that students don't interpret it the same way. So this equation, notice that the plus 7 is above the fraction bar as well. I have an extended fraction bar with x plus 7 on top and division of 5 on the bottom. This is completely different than the one we had previously. Again, the one we had previously, if you remember, I'm going to write it more over here. The previous problem was x over 5 plus 7 equals 11. And many students will look at the previous problem and this as being the same thing. That's not the case. The reason being is that the way that this is set up here in the way it's being structured, it's indicating that the x plus 7 is grouped together. So contrary to typical order of operations, the addition of 7's being done to the x first and then the division. Whereas over here on the left-hand side, the division of 5 is done first, and then the addition of 7 is added second. That changes the order in which you have to eliminate these things. And that's what's important, because that's going to change your answer. So there's two ways to approach this. I mean, the first option is it'll still treat this as a two-step equation, is that, I still treat it this way, but I realize, okay, in this instance, the division of 5 has to be eliminated first. So I would multiply both sides by 5 first to get that x plus 7 equals 55. And then I would subtract 7 from both sides to get that x equals 48. The other option is one that we're going to spend more time with in the next part of this review for the remediation course, is that even though I'm looking at it as a fraction up here, I can distribute this division of 5. Division is just as distributable as multiplication, because in algebra, division is simply multiplying by a reciprocal. So as you do this, I'm just going to rewrite this as x over 5 plus 7 over 5 equaling 11. So, it makes it a little bit more, problematic with extra fractions, but, if you have no qualms with fractions, then there's nothing to be worried about. So if I go through and solve this equation now there's no parentheses that are changing any orders of operation. I do have a division of 5, and I have an addition of 7/5, of which the first one that has to go is the addition of 7/5, and I would accomplish that by subtracting 7/5 from both sides. So when I do that, I would have x over 5 equaling 11 minus 7/5. Of course, to carry through that subtraction, I'd have to have, 11 rewritten as 55 over 5, so I have a common denominator. And 55/5 minus 7/5 is 48/5. So that leaves me with the equation x over 5 equals 48 over 5, which I can already see since they're both being divided by 5. I can see that x would have to be 48, but just to finish it more systematically, I multiply both sides by 5. That would cause the divisions of 5 and the multiplications of 5 to cancel out on both sides. And I do get that x equals 48 again. So there is more than one way to often, as you get more complicated equations, there's often going to be more than one way to go about solving it. It's just that as you go about solving it, you have to make sure that what you're doing is legitimate for the stage where you are, and you know exactly why you're allowed to do what you're doing. If you're just doing something for the sake of doing it and have no reason as to why you're doing it, that's probably an indication that you're going to be making mistakes on it. So the very last one that we're going to be looking at in this practice is 55 equals 8d plus 9. So give it a try and we'll go over it. Okay, so 55 equals 8d plus 9. Now, again, I'm going to add the extra step because I just my preference. I prefer having the variable I'm solving for on the left. So I'm going to change this to 8d plus 9 equaling 55. And so when I look at this, I have a multiplication of 8 occurring to the d, and I also have an addition of 9 occurring onto the d. So that's the order in which they would occur. So when I start undoing them, the addition of 9 has to go first. So subtract 9 from both sides. And when I do that, I get that 8d equals 46. Again, 8d means 8 times d. So to get rid of the 8 and isolate the d on the left, I'm going to divide both sides by 8. So D is going to be 46 over 8, which I can then simplify to be 23 over 4 as an improper fraction. Now I have a couple of options here because there were no fractions or decimals given here. And again, if it was like a multiple choice item, that would kind of dictate which way I'm going with it. But I could either rewrite this as a mixed number because, 23, if I carry through the division and do 23 divided by 4, I would have, as you can see down here, 5 times 4 would be 20. I have the remainder of 3. Now, that allows me to go right to here and say, okay, 5 3/4. Now, if you know it's 5 3/4, you know it's 5.75, but in order to show that, just to kind of give you a recap of that, I'd put the decimal point here, say, okay, let's put a 0 down, bring down the 0 here. 4 goes into 30 7 times, that's going to be 28. Still have a remainder, and, so I'm going to add another 0 here, and bring that down to have another 0 here. 4 goes into 25 times, and you can see at that point I would get a remainder of 0. So yeah, that's what you keep doing. Either you get a remainder of 0 until you see a repeating pattern. But you can see here either is the same answer. And that's the end of these. If you have any further questions, please make sure to contact me. Until next time, have a good day.